we've talked about before how the photoelectric effect and shows us that light acts as a particle, and we also have had the EMR spectrum, so light acts as a wave. The first scientist who actually started figuring out how it can be both was Niels Bohr, and he proposed a model that linked the atoms, electrons with the photon emissions like they saw in the photoelectric effect. In his model, he suggested that the electrons are arranged in specific orbits around the nucleus based on their energy. And so you have this picture in your note packet. This is an example of hydrogen, where we know it's hydrogen because there's just one proton in the center. And he thought that the orbits, or the areas in which the electrons were circular, which we now know they're not necessarily circular. So this is not necessarily true, okay? But the energy levels, which are the orbits where the electrons can be, are kind of like rungs on a ladder. So Bohr thought that they just kept going out at the same increments as they kept going. So those fixed energies are called energy levels. We still use the term energy level to this day, but it is not, this model doesn't work, because we found that it works perfectly for hydrogen, which is one electron. But when you move up to helium with two electrons, it no longer works. Okay? So the definition of a quantum, which we've had this before, a quantum of energy is the amount of energy required to move an electron from one energy level to another. What we have found, though, is because it's not like the rungs of the ladder, that the amount of energy an electron gains or loses is not always the same, because the energy levels are not always equally spaced. Okay? So a quantum is just a word to describe how much energy you have. Okay, so the two guys who have since discovered what our modern model of the atom are Schrodinger and Heisenberg. Heisenberg had an uncertainty principle which states that it's impossible to determine both simultaneously the position and speed of an electron. It's like if you look at like the newspaper and they have the football player on the field, and you can see like maybe they're at the 25-yard line because the picture will show you the yard lines, but you don't know how fast the football player is running. Okay, so it's kind of like that, where you can know one or the other, but you can't know both. You might have heard of like Schrodinger's cat in the box problem, and that's what it is. Like if you have a cat inside a box, you could know it's inside the box, but you don't know if it's alive or not. That's what he never really did it, but it's like the theory he came up to like reason this. Okay, and then Schrodinger's wave equation gives us answers to know that electrons do indeed have both a wave and particle-like nature. Okay, so only electrons that have specific quantities of energy and frequency provide solutions to Schrodinger's equation. Now, Schrodinger's equation is not an equation we're going to solve, because it is very super complex calculus that I did not even get into until like my senior year of college. Okay, so the equation, this is a question on the test and asks, what does the equation give us? It's not a math equation that we're going to solve, but we're going to use the results from it. And what Schrodinger's wave equation gives us is the quantum mechanical model, the 4 quantum numbers that make up that quantum mechanical model. So that's a question on a worksheet you're going to get in a little bit, and that's a question on the test. It gives us these 4 quantum numbers. Okay? So it tells us that the probable location and motion of electrons can be described in terms of 4 quantum numbers. And this is an L. I know it looks like an E, but it's a cursive L. M and S. We're only going to discuss M and L because that's what we need to know for the stuff after this. But I'll kind of describe quickly what the M and the S are. It's just some stuff that's not state standards anymore, and it's not on the AP exam either. So I decided to skip 2 days worth of material so that we can cut it back. Okay? So the first quantum number is the N quantum number, the principal quantum number. This designates the energy level of the electron. So it describes the size of the space, which the space where the electron is called an atomic orbital, and so it describes where it is and how it moves. Okay? So N is a whole number that begins with 1, and it currently ends with 7. And the reason why it ends with 7 is because of the periodic table. We're going to talk about this chapter, like why this is shaped the way that it is, okay? And all has to do with these electrons. So currently, down here on the side, there are 7 rows on the periodic table. And that's to show that there are 7 energy levels, okay? If we were to discover like element 119, that would probably go under francium, and so that would be an 8th row, so then that would be an 8th energy level. But we just don't know about it yet, so that's why we say it's currently 7, okay? The value, as n gets larger, the energy associated with it increases, and the average distance of the electron from the nucleus also increases. And that makes sense because down low on the periodic table, they have a ton of electrons. They have lots and lots of electrons and protons that are making it up, so they need more space to fill all those subatomic particles in. So that's why that is the way it is, okay? You all good if we move on? Yesterday I was going too fast, and so I'm trying to be a little bit slower. Okay, the number of electrons that occupy each atomic orbital is equal to 2 times n squared. You will not have to know that little formula. You just need to know, like, when any energy level equals 1, it holds 2 electrons. Remember, you can use, like, the E negative to say electrons kind of thing. And n equals 2 is 8 electrons. That all comes from the periodic table as well. So, if the first row is the first energy level, and I said that it holds 2 electrons, well, across the first row, there are 2 elements. And then in the second energy level, in the second row, there's 2 on this side and 6 on this side, so that's a total of 8. Okay? So this shape, which we're going to get into either today or tomorrow, is all because of the electrons. Okay? And when you get down to 5, 6, 7, those kind of change a little bit, and that's because we haven't discovered all these new elements yet. Okay. The secondary quantum number is the L. Remember, this is an L, not a cursive E thing. And it's also known as the angular momentum quantum number. This tells us the shape of the region in which the electron is occupying. The values aren't really important for us this year. This is something I took off. But it can start with 0 and goes up to the quantity n minus 1. We do need to know the shapes, though, that are associated. So the angular momentum quantum number is giving us what shape the region is in which the electron's moving, okay? And so these shapes are called sublevels. So the first sublevel is S, and that is a spherical shape. And you have these pictures in your notes, okay? And P is the next one, and that shape is a dumbbell shape, like when you're lifting weights. I did not come up with these names, because dumbbell doesn't really look like that, but you know, whatever. The D sublevel looks like a clover, and the F sublevel looks like 2 clovers put together.
Do we have to put it as a small d, like in lowercase?
No, you can make it bigger. So the shape, this might be like a multiple choice question, and it might say like, which shape is associated with the P sublevel? And you would have to say, oh, P is dumbbell, and you'd have to pick that, okay? So these are the regions, instead of just being circles, like Bohr thought, these are where the electrons are moving in that area, in that like clovery area. That's where the electrons could be, kind of thing, okay? So it's a little bit different. Now, in that same area in your notes, because I forgot to put this in, you need to write this next slide down, okay? Every sublevel can hold a certain number of electrons, and this is going to be important for us today and tomorrow. So an S can hold 2 electrons. Remember, you can use like the E negative. P's can hold 6 electrons. D sublevels can hold 10 electrons, and F sublevels can hold 14 electrons. Just write it somewhere where you have space. Wherever you have space is fine. We're going to refer back to this in just a second. So the 2, the 6, the 10, and the 14 are special numbers that you're going to see a lot this chapter. So so we talked about the first two of the four quantum numbers. The second two we are not going to be learning about, okay? And that's because they are no longer state standards. They're beyond the scope of the course. But if you wanted to know, you can research it more. The M, yes, like it's too complicated for chemistry one.
Star Wars.
Sure. So M and S kind of are, if you think about like how the Earth orbits the sun, the Earth has a specific orbit, like a trail that it's going, right? That would be like the M quantum number. And then as the Earth is orbiting around the sun, it rotates on an axis. And so the S quantum number is kind of describing how the Earth is spinning around its own axis as it orbits. So that's what those two quantum numbers kind of tell about the electron. But we're not going to talk about it because we don't need to know that. What we do need to know are atomic orbitals. Excuse me. And these are made up from the two quantum numbers we just discussed. So the number in letter in each atomic orbital comes from the quantum numbers. The number could be 1, 2, 3, 4, up to 7, tells us the energy level that the electron is in. And the letter, S, P, D, or F, tells us the shape or the sublevel in which the electron is traveling in. Okay? So these numbers and letters, these atomic orbitals, are how we're going to show the electrons are filled in each atom. Okay? Did we get all our blanks filled in?
Yeah.
Yes. Okay. So the electron configuration is what we're getting into now. What we're doing today is really technically called orbital notation, and then tomorrow or today at the end, we will talk about electron configuration. Okay. This tells us how the electrons are arranged. So somebody today asked me, like, okay, Ms. L, why do we have to do all this if we look at the atomic number and it tells us the number of electrons already? We're describing where the electrons are located in the actual atom with this, okay? And so this is why we can do that. We're trying to explain where the electrons are located for each atom. So electron configuration diagrams the electron structure and how the electrons are arranged, in what energy level they are, and in what sublevel or shape they are traveling in, okay? So we have 3 rules that help us fill atomic orbitals. And we're going to talk about the first 2 first to do orbital notation, and then the third is with electron configuration.
Is something supposed to be like in energy levels?
What?
Like the 2 dots?
Yeah, I'm going to have like the next couple slides.
We'll
Are you ready to go? What?
We know that we need to write it down.
You're not going to write anything down.
Oh.
You don't. Okay, so the first rule is the Pauli exclusion principle. This is what we're going to be doing, okay? So notice how the atomic orbitals, the 1s, the 2s, the 2p, those are the atomic orbitals, and we are filling in electrons as arrows to show how many arrows or how many electrons are in each orbital, okay? Pauli exclusion principle tells us that no 2 electrons have the same exact set of 4 quantum numbers. If we were doing quantum numbers like I used to previously teach, you would see that. But we're not taking the 2 days it takes to learn that now this year, so it's a little bit different. But we do need to know that when we put electrons in orbitals, they can't be in the same direction. They have to have opposite spins. So the up arrow and the down arrow is showing how they have opposite spins, okay? Sometimes, like I'm going to do it this way, you might see this in other places, that it will be kind of like a half arrow instead of a full arrow. Full arrows are completely fine, half arrows are fine as well. You just have to show the direction of spin and they have to be opposite each other, okay? So Pauli exclusion principle is telling us that we have to have opposite spins, and when you fill in, you can't move past a vertical barrier until you have the orbital full, okay? The other rule that we have to know is Hund's rule, where we are going to occupy our energy levels, okay? And as you go, like 1s you can't move on to 2s until you have 2 electrons in there, and 2s you can't move to 2p until you have the 2 electrons in 2s. When you get to the p, I call this like the teeter-totter rule, okay? You don't want to have all the electrons overloaded on one side. You want to have them kind of evenly distributed. So in the p orbital, you actually put 1 in each location, pointed upward, before you can put a down arrow anywhere, okay? So you will have to have 3 in the p's before number 4 will go down, okay? And we're going to see how this happens with that worksheet or the handout that I just gave you, okay? So grab that. After we'll do this first, and then we'll do that. Okay, so the number of arrows that you're going to put in is dependent upon the element. So this is why you might need to look at a periodic table, because we need to know how many electrons the elements have. So how many electrons does carbon have? 6. So that means that we're going to have 6 arrows. When we're done with our 6 arrows, we're done with the problem, okay? We start with 1s, and we fill our arrows in, and we can't move to the next sublevel until that previous sublevel is filled. The p's are a different story, okay?
I don't know how many go in.
Looking at the periodic table, carbon has atomic number of 6.
I know.
And so that's how we know, because carbon is the problem.
Yeah.
Okay, so 1s, you're going to put an up arrow first and a down arrow. Only 2 arrows in that sublevel because it is an S, and that is a full sublevel. But we only have 2 accounted for, and we need 6. So then now we're going to cross the barrier and move to the second one. Okay, it's only 1 box, so we put 1 up, 1 down. That is 4 out of our 6. So we are almost done, but we still need to do 2 more. So we'll move on to the P sublevel. Okay, now with the P, this is the teeter-totter. We're going to put 1 in the first box, pointing up. But the second one does not go in the first box. The second one is going to balance out by moving to the second box, also pointing up. Okay? And so, yes, I know that this is not completely even. There's, like, you don't have anything in the last one, but that's okay. It's supposed to be like that because we have 6 arrows, 6 electrons are accounted for, so we are done with this. If we added a 7th arrow, that would mean it's no longer carbon. Okay? Last but not least, unpaired electrons are when you don't have a down arrow with the up arrow. So how many unpaired electrons do we have? 2. And that comes from right here.
Why would they be both up?
Yeah. They have to be, once you commit to putting the first arrow up in every box, anytime that you move to a new box, it always has to be up first before you go down.
So how would you choose to make that one, the first one up?
Just, if like this first, you just make the choice. If you say it, okay, first one's up, then every single time the first one has to be up.
So, like, if we did it like first one's down and then the second one's up.
Then all of the first ones would be down then, yeah. Okay, so now let's look at that handout that I gave you, okay? It all depends on the number of electrons, and this does go in the order of the periodic table in the start. So how many, what does H stand for? Hydrogen. And how many electrons are in hydrogen? 1. So that means that we're just going to have 1 arrow, okay? And so we'll start in the 1s, and we'll put our 1 arrow up. Okay, and that's it. For helium, how many electrons? 2. So we need to have 2 arrows. So the first one will be up, and the second one will be down.
Do these go in order?
They do. Lithium is next, and how many electrons does that have? 3. So we will have, the first 2 will look exactly like helium, up and down, but then we'll have to move to the 2s now, and we'll put the first one up. Okay? So if you get the hang of it, that's fine, but I'm going to keep going. I only have 3 nitrogen up here. We need to fill the whole paper. So beryllium is 4. So 1, 2 in the first one, 3, 4 in the second one. Okay? Boron is when we get to the P, because there's 5 electrons. So 1, 2, 3, 4. And when you get to the P's, I know on your paper it says PX, PY, PZ. You put 1 in PX. And that's it for boron. And then carbon, we just did this one. We put the first 2, the second 2. And then for the last 2, you put 1 on the 2px and 1 on the 2py. Okay? And then nitrogen, with that 7, we go 1, 2, 3, 4, 5, 6, and the 7th one is on that last 2pz. Okay? So I don't have it up here anymore, but oxygen is when you can start going back and putting the down arrow so that the 8th arrow and oxygen will go back and be down on the spot. Okay? You should not touch 3S on this paper until you get to sodium. Okay, so let's take a second and fill this in. Don't worry about that other column right now. We just need to fill in the first column.